Hi everyone, this is Tying Cheng. Today, I'm here to present our work 3DMiner, Discovering Shapes from Large-Scale Unannotated Image Datasets. This work is partially done during my internship at Adobe Research. Learning-based systems that try to infer 3D geometry from images suffer severely from the amount of available 3D data. On contrary, the scale of 2D image datasets are much, much larger. While the vast quantity of 2D images online captures rich information regarding textures, shapes, and relationship between objects, there lacks a technique to leverage this information and create a general, high-performing 3D reconstruction method. In this work, we present a pipeline named 3DMiner to target this problem and mine 3D shapes from challenging large-scale unannotated image datasets. Here is a brief overview of our method. Our approach leverages the recent advances in learning self-supervised image representations to cluster images with geometrically similar shapes. Specifically, we propose an inference time augmentation scheme to obtain variations of one image and mitigate slight rotation changes, then use DynoVIT and agglomerative clustering to obtain common image correspondences. Within each cluster, we again apply DynoVIT, but on a pixel level to find co-segmentations of images. These co-segmentations allows us to draw key points and subsequently obtain rough camera estimates through rigid factorizations. These estimates are used as initialization for bundle adjustments. Finally, for every image cluster, we apply a progressive bundle adjusting reconstruction method to learn a neural occupancy field representing the underlying shape. We add two regularizations, one on the smoothness of depth and the other on the space annealing to ensure that the shape is properly reconstructed at the right place. We present some of the quantitative and qualitative results of 3DMiner. In this table, we show our comparison on Pix 3D chairs, one of the harder dataset and categories for single view reconstruction. We align the meshes to their ground truths via coherent point drift and compute the chamfer distance and F1 score. We select these three subsets of images using a threshold on the reprojection error within each cluster. On the full Pix 3D chairs, 3DMiner improves by 33% in chamfer distance and 10 points in F1 score. And the performance increases significantly when we use our selection criterion. In the following figure, we show 16 objects reconstructed from Pix 3D and Lion 5B, with 4 objects particularly highlighted in the top row. Objects 1 to 6, as shown in the bottom diagram, show reconstructions with high fidelity when clusters are very accurate. 7 to 10 present generic shapes captured when the clusters are more diverse. And finally, 11 and 12 are results on very challenging non-rigid objects. We plot the reprojection per cluster, which is averaged over each image in the cluster in ascending order, and show representative reconstructions for 4 data points. We empirically observe that the reprojection error is a good indicator of the quality of reconstruction. Finally, we show the t-SNE embeddings of Pix 3D images embedded with DynoVIT with and without augmentation scheme. The 2 rows represent clusters on the entire dataset and on the fine-grained category of Pix 3D chairs, respectively. Each color denotes a different object. Note that with augmentations, images corresponding to the same 3D object are grouped together, forming clusters on a single color as shown in the right column, which is not the case without augmentations as shown on the left. We present some of the example clusters from Pix 3D chairs as the following. And that's it. Thank you very much for listening to our presentation on 3DMiner.